It's time to start. We will do that. So today I haven't found any news due to disasters. People in India don't have any money. People in the United States have a new president and they're out on the streets protesting. They don't want this president. And we're waiting for whatever number 3 comes along, but hope it doesn't come along too soon. So I would like to start by going over that problem that you were working on at the end of the session to see how you are doing with that. This was a fatigue problem where you're giving this data. Unfortunately, as I said, it's in engineering units because all my plots are on engineering units, but you want to get some DADN versus delta K data for that. And here's the data. You have a number of points, and we were going to do a secant, that is take adjacent points and get the ADN between adjacent points, and then do delta K from these points. Now, I have to go to my solution on Word document. I took one pair of points as example, and then we'll look at all the points. So number 5 and number 6, again, you have to do between adjacent points. So this is the difference in crack length. This is the difference in cycles. Divide that difference, 0.060, by this difference, 30,000. I got 2 times 10 to the minus 6. Now for the K, you need a crack length, you have the load range, you need that table. And by the way, did you get to upload any of the pages yet? Did it come?
Yeah. Have you checked? Yesterday, I'm not checking.
In the modal? Didn't make it yet? We'll ask Mahir sometime.
Check my moodles. Was there like that? No. Yeah. Nobody had checked. They have uploaded.
They have uploaded.
First day is
Yeah, but not the rest.
not the rest.
You need, yeah, well, the first day helps a little bit, but you need some of this.
Yeah.
Okay, go back to what I was doing. To get the K, then you need the session 2, F calibration, little f, and then you should take an average crack length. That works better. If you take the bottom one, it's a little bit low, and the top one's a little high, so take the average, and that was 0.76. So A over W, 0.38. Again, a very short crack to start. This is the F factor. The delta P gives the delta K. It is from 100 to 1,000 or 900. Put them all, then load P, little f, divided by thickness B, divided by square root of W. This is in then PSI root inches, since this is in pounds. If you're not familiar with that, we use KSI kips, meaning 1,000 pounds. So I changed from pounds, PSI, pounds per square inch, to KSI, kips per square inch. And then this was this point right here. So I went back to the whole set and did each one. For the corresponding DADN, get a delta K. And all the way, so you could do each pair of 2. And if you want to do the other method that I told you about, incremental polynomial, you actually need a fitting program. So you have to do that on your computer, or if you have a fancy calculator, you'd have to do it on a fancy calculator. If you want to do by hand, this is obviously the easiest to do. Okay, I want to do then, I took all those points and plotted them. When you plot, you should plot on log paper. And this is supposed to be delta K. It was my software at the time, couldn't write delta. I don't know why it wrote that little 2, but couldn't write delta. Anyway, this is what the data look like. It forms a fairly straight line, and in order to get the constants that go in the Paris law fit, d/n is c coefficient delta k to the exponent n. You need to plot using logs. So I did here using logs. No. Almost had it. So to plot using logs here, then you can do a linear fit. And in the linear fit, the exponent is the slope. So the slope 2.507. In fatigue data, all those digits are not necessary. So 2.50 is what I used here. And then the coefficient be the inverse log of that. Now I use base 10 log. You could use either one. It would fit either, but base 10, I did that inverse. So that is then d/n and delta k. So this is the approximate fit. This is what we call the power law fit, or some people call the Paris law fit. And I'm going to use that later in some things. Maybe not. I think tomorrow we'll use that. So if you want to write that down and keep that, you can do that. Now I had also on here a second problem. The second problem was this: if the threshold is 5, what load range would you have to stay below to not cause crack propagation? So you want to be below the threshold in terms of delta K. And so I did it just at the limit and said that then my load is going to go from 100 to some unknown value at the top. And that I have, I hope. On the Word. Okay, I think you can see this. Okay, so the delta K is 5 is the limit. And then I said for the initial crack of 0.6 inch. So A over W is 0.3. F is a fairly small value, 5.62. Putting that together, then delta P F B squared of W equals 5. The unknown is the delta P, which came out in terms of kips, 0.315 kips, or 315 pounds. So then the load range 100 to 415 is that 315 range. So stay below 415 and you should get no crack growth from delta K threshold point of view. Questions on this? In order to get through that, you have to do a lot of work. Did anybody get numbers that weren't any good? Or you don't want to admit it? You get some good numbers. Okay, I want to do this. have here a problem that is illustrates something that comes up a lot, and I waited a little bit long to illustrate that, but I want to illustrate it here, and also I want to bring up this. You have your own copy of this, so if you can't see it on here, you should look at your own copy. But for a given A over W, this is the little f that we use in the K calibration. Here was another column that I hadn't explained yet, so I want to explain that, and we're going to play with that for a few minutes because it's a valuable thing. And in order to explain it, I think I'll go right on the board here. And I have this so that you can hear me, I hope. In almost every test that we do, we plot load versus displacement in the K1C test, and you can do that in fatigue. And if you get a linear slope, you know then that you are in the linear elastic range where K works okay. So load P, displacement V, this slope is P over V. So what is worked with rather than P over V, the slope of the load, is the inverse. 1 over the slope is called compliance. 1 over slope then has units like this. Length, V is a length, and P is a force. So length over force. Now, in the tables, everything is written to be unitless. So to get rid of length over force, write BEV over P. So in this case, B, as you know, we use for thickness. E is elastic modulus. So elastic modulus. Then units here would be B is length, E is force per length squared, V is length, and P is force. So then you can see 2 lengths on top, force on top, 2 lengths on the bottom, length squared on the bottom, and force, and that's no units then. So that's the compliance
compliance story. For every A over W, there's a corresponding compliance. And that corresponding compliance can be used if you go into the test record itself. If you're doing a test and look at the slope and then know the modulus and the thickness, which you usually know the thickness, the modulus, steel, you can take a general value, or aluminum or whatever, take a general value, and you get this BEV over P table. Now I want to do a problem with that to show you something that is unique in crack body.
So back to if you have your table that, or that page of handout, you might want to follow along on that. So I made up a problem like this. Get K values at initial crack size and crack size plus 0.2 inches. Load is in kips, dimension inches. E is 30,000 KSI. That's our normal engineering units for steel. The compact specimen, B is 2 inches, or W is 2 inches, B is 1 inch, A is 1 inch, and the V, that stands for load line. You can imagine that plot over there, this thing, the displacement depends on where you place the gauge. If you place the gauge far from the crack tip, you get a different value than if you place it close to the crack tip. The table in the handout, BEV over P, that you have is for load lines. It doesn't say that, but that's what it's for load lines. And very often people put gauge on the load line. You'll see how you can do that in next week's lecture. Anyway, we want to do this and then let the crack grow a little bit and do it again. So the initial A over W is 1 over 2.5. We know what the F is. You've used that one before. But the BEV over P is 36.98. You have to look that up in the table. And I can show you where that is for this one case, maybe. So for A over W 0.5, it would be right down here, right at the very bottom. You see that one? Okay. Then let's go back to where we were. So then you can calculate K from the displacement, but it takes 2 steps. You have to back out a load. We didn't know the load, we just knew the slope, but no load. So having known the slope, you can back out the load. So rearrange that to make it BEV over that value, 36.98. So B was 1, 30,000 for the E, and the displacement was 0.006. This is 4.87 kips, or kilopounds, thousands of pounds, so 4.87 thousands of pounds. So then when you back out the load, you can go back and put it into the case equation, because now you have a load, you know the little f, and you just calculate the K, 33.25. Now, I said in the problem, what I want to do is go back and change the crack size by 0.2 inches. Originally it was 1, now it's going to be 1.2. And I'm going to hold the displacement constant. I don't know if I mentioned that in this problem. So displacement holds constant. So the final crack size over W is 0.6, new value of F, a new value of BEP/V over P, and again, then same displacement, 0.006. I have to back out the load, 2.845. Notice the load drops significantly. So now the K, when I put the load in there, has dropped to 27.5. So this is one of the fundamental things in crack bodies. If you have a constant displacement with a growing crack, the K is always dropping. If you have a constant load with a growing crack, the K increases. So it's kind of opposite. Constant load, K increases as the crack grows. Constant displacement, K decreases as the crack grows. That decreasing K is a valuable thing. It's used in a lot of cases and in some test methods. So wanted to go over this and then show you how it would be used sometimes. So I don't need that right now. And good. Questions on that? Yes.
Sir, this was a problem, but for practical problems, how
Yeah.
can we decide N? It's, after how many cycles we have to check the crack length?
How can you?
After how many cycles
Yeah.
we can check the crack length? How to decide that in a practical situation?
How do you decide the
Capital N.
capital N?
Number of cycles.
Oh. Yeah. In a test machine, you should have a cycle counter.
Question he's asking is after what increment of n you will measure the crack?
Oh, okay. Yeah, I get that. That's kind of up to how good you are. If you're measuring it by microscope, and you want to do it as the test goes on, how fast can you do that measurement? If you want to do it in when you have another measure, like we use this compliance now, this is how you use compliance to measure the crack length. One of the things we talked about yesterday. You can do it continuously. So it would measure continuously. More often, I think, though, you don't measure it after a number of n, but after a number of a certain crack advance. So you might like to do it every 1/10 of a millimeter or whatever, you pick some crack length increment. So, you don't want thousands and thousands of data points. Some people do, but normal people don't want thousands and thousands of data points, just too much to handle. So you could say that every time the crack grows 0.1 millimeters, I'm going to take it 0.5 millimeters if you're lazy and don't want to take it too often, something like that. But I think it's more important to take it after a number of amount of crack extension. In the old days, though, I think your question probably is more important because people used the microscope to look at it. And they didn't know when it went 0.1 millimeters or 0.5 millimeters. So they would say, let's try it. Depending on what range you are, fast crack growth or slow crack growth, you would say, maybe 1,000 cycles. They usually stopped it. And then they'd cycle it, and they'd often stop it at the maximum load. Then the crack is open, and you can see it better. If you stop it at the minimum load, you can barely see the crack. It's very hard to see visually anyway. People use all kinds of tricks. I don't know, have you done testing or think about testing? Do you know a strobe light? Stroboscopic light is a light that blinks. Boom, 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 boom. So some people set up a stroboscopic light on the specimen so that it would blink at a certain point of the cycle. If you are doing 10 hertz, say, 10 cycles per second, you might have it blink every second. So you'd have this, and then it would be open and you'd see it, or every 9.9 of a second, and then you could see it. Doing crack growth rate in the old days wasn't real easy. It's easier now. With people mostly are using the slope now, so it's much easier.
I have a doubt. This compliance is within elastic range, it is constant?
In the elastic range, the compliance changes as the crack grows. So, as you would see on that table,
Yeah.
as the crack grows,
Yeah.
the slope gets lower, but the inverse slope gets higher. So the slope keeps changing continually as the crack grows. What happens, or what can happen if you use compliance, is you wear out your gauge. You put this little clip gauge with strain gauges on it, and then it's there cycling like that, and you can fatigue the gauge sometimes. I don't know if you're a tester. One of the challenges in doing tests is to test your test specimen rather than your equipment. People often fail their equipment rather than the specimen, which isn't good. Even in a tensile test, you have a tensile test with a gauge length, and it fails outside the gauge length. You have crack growth, and you break the loading pins and not the specimen if you're careful. But that's one of the things. If you are just learning testing, you often break your equipment. Once you get used to it, you design the equipment better sometimes. Other questions, comments? This is then the next logical step. You learn the K, which is our parameter. You learn fracture toughness, which is failure under monotonic loading. You learn fatigue, failure under cyclic loading. And now, lastly, environmentally assisted cracking, which is environmentally assisted cracking. Stress corrosion cracking is the old name for this. You apply stress and an aggressive environment that may cause stable crack growth under no cyclic loading, but just under a constant load. And in this case, the most useful thing was to have a threshold value that if you stay below that, you don't get crack growth. In the older slide, that was called K1SCC, K1 for stress corrosion cracking. Now, the newer name, K1EAC, K for environmentally assisted cracking. And also show you that an aggressive environment also influences the fatigue crack growth. Way back when, soon after fracture mechanics was invented by Irwin, they did this test. They got a high strength steel. If you can just look at the numbers relatively, 245 KSI yield is really high strength. It's getting close to 2,000 MPa yield strength. It's very high strength martensitic steel. They used the center crack specimen, which is the Griffiths geometry, and they loaded the specimen to 75. Now 75 is less than 1/3 of that value. So they loaded it only a small fraction of the yield. So yielding wasn't a problem at all. It was well within the linear elastic range. For each case, they put in some environment. Recording ink, distilled water, all different kinds of alcohols, and all these environments. I don't know if you're familiar with all of them, but alcohols and oils and so forth. And then they watched to see if the specimen failed under that fairly low stress and at yield strength. And this is time to failure in minutes. So anywhere from less than a minute to maybe, in some cases, a few hours, and it failed in that time. One of the things people learn from this is that you can fail a material due to a bad environment. The other thing, back in the early fatigue days, people sometimes put recording ink into the crack to mark it. Now, I don't know if you ever ran XY recorders. We used to run them with a pen. I told you back in the old days you had this pen with in a chart where you had an XY plotter, and the pen always clogged when halfway through the test. So you had to unload it and start over again and unclog the pen. Anyway, they decided it wasn't a good idea to put recording ink in the crack because that's influencing it. So if you want to have a crack growth that is an air, you don't want recording ink in there. Here was the old time, the original test setup for this. And the test setup was this. They put a specimen here. It's cantilever, like a cantilever beam. That is, cantilever is fixed on one end and free on the other end. And then they attached some kind of a beam to it that wasn't part of the specimen. And then they put a load pan. So if you've ever seen creep tests, it's similar. You put load here, and then you get a big bending moment on the crack there. Now the crack was put in by fatigue. So before they put this contraption together, they would put it in a test machine and fatigue pre-crack it to get a fatigue crack here. And then they'd put the contraption together, and then they'd put some kind of a chamber around it. And it could be a simple chamber if it was a simple environment, and then start putting load on there and just wait to see how long it took to fail. So they'd start adding load on there and sit and wait, and then eventually it may fail or may not. Here was a test on a titanium alloy. This was titanium, 7 aluminum, 1 moly, 1 vanadium. I don't know if you know that. This alloy was originally chosen way back when the United States was going to build a supersonic airplane like Concorde. I don't know if you've probably seen the Concorde flies Mach 1.5 or Mach 2 or whatever, pretty fast. And the United States was going to build that. And most of our government projects go like this. The government keeps putting money into it and funding it until it works, and then they decide they didn't really want it in the first place. So they were funding this until it was almost complete, and then they decide, oh, they didn't really want it in the first place. So they stopped funding. And that's a lot of our government projects happen that way. Anyway, this was chosen because they thought it was immune to corrosion. And general corrosion, which is things that attack a surface, like rust in steel or pitting or whatever in some of the alloys, general corrosion and this, stress corrosion cracking, are quite different. General corrosion happens usually on a surface, but this happens inside the material. And in this case, then, they loaded specimens, probably used this apparatus, and then they waited some time and looked for failure. and you can see that the time they waited is in the order of a couple hours at the most. And then if they got no failure, which is what they got with these little arrows, these K values had no failure. The K values above that had failure, so they drew a line below that and called that the K1SCC, or the threshold value, that if you stay below that, you won't get crack growth in environment. The environment here was seawater, and the seawater thing is of interest to the Navy, but also for other things like, I guess they were thinking airplanes flying over the ocean would get a seawater type, or exposed to seawater type thing. A lot of big power plants that we have are near water that use for cooling the power plants, and it could get seawater in it. So seawater was of big interest. They usually make seawater that is not real seawater, but is made up seawater with 3.5% salt. Now, this test was standardized and last done quite a while ago, so I don't know how it's doing now. But this is an ASTM test 1681 for threshold stress intensity factor for environmentally assisted cracking, KEAC. In that, they measure a KEAC or K1EAC. They use the cantilever bend specimen or the compact specimen. They're pre-cracked, and they use usually constant load or step load. That is, you put a load on and wait a while, and if nothing happens, put another load on and wait some time. The test time, though, for steels, high strength but not really high strength, was 10,000 hours. 10,000 hours is a little more than a year. For really high strength steels, 5,000 hours. That's a little more than half a year. And in aluminum alloys, again, 10,000 hours. Titanium, 1,000 hours. Titanium seems to either crack quickly or not at all. So that's that. Now, they had two numbers, KEAC or K1EAC. To make a KEAC be a K1EAC, they went back to the K1C E399 requirements, and essentially the 2.5 K over the yield strength squared, if they could meet that, that is that the thickness and the crack length were greater than 2.5 K over the yield strength squared, then they put a 1 in front of it. If it didn't meet that, they didn't put the 1, they skipped a 1. So I don't know if it's a big deal or not. I hadn't worked on this standard, so I don't know how important that was. Now, the thing I just showed you came up to be important in doing the test, but never made it into the standard yet. If you use this apparatus, that's fine. That doesn't do any harm to any equipment because it's just sitting on its own. But most of the compact specimens would have to go in a test machine, and if you put it in a test machine and wait 10,000 hours, that's a long test. And most test machines in US that people buy cost more than $100,000. So if you are taking a $100,000 machine, having a test sit there for over a year without anything else being able to test, it's kind of a waste of that money for the test machine. So they wanted to have another way to test that wouldn't use up a machine, and they came up with this idea of the bolt load specimen. So I'll show you that. Here is the compact specimen type, and instead of having 2 pinholes like you would do in a fatigue test or a K1C test, they put a hole here and then they thread it from the top down and put a bolt in there, and then they turn the bolt against a half pin. This is only a half pin. So you turn the bolt against the half pin, and load it that way. So you load a specimen with a bolt turned against a split pin, as you saw in the figure, and then measure initial displacement. The reason for measuring displacement is this apparatus doesn't have any load cell, so there's no load capacity in here, and you have to then measure displacement and use all this mess that we talked about over here, the BEV over P column, and get then back out the K, so you get the load and then the K from the load. So you measure displacement. Once you have this specimen loaded up like that, it's kind of free then. You can put it in an environment chamber and you don't need a test machine at all. So it saves you from using a test machine. You put it in an environment, you can put it in seawater, you can put it in a closed chamber and put something like hydrogen gas or some other gas if you're interested in that, and just leave it there, and it's okay. It just sits there. At the end of the test, then you have to take the specimen out, unload it, and then somehow break it open. Now we'll talk more about breaking open specimens. If you're testing steel and you want to break them open without much damage, the thing to do is to drop them into liquid nitrogen bath or something very cold. If you put them in a very cold bath, then they get brittle and they break open easily without any deformation. If you try to break them open at room temperature, sometimes you get a lot of deformation and yielding that distorts the features of the thing. So you want to break it open without much happening. So then you have to break it open to get the final crack length and use these calibrations that we just played with to get the K. So that's the bolt load test. It's fairly interesting or good test method. So I'll show you a sample calculation. This is almost what we just did. So just to show you again, so say you took this specimen, you put the displacement gauge out front, and you measured 0.01 inch, and then you know the material is steel, say, and you pretty much do these calculations after the fact because you can't get the initial crack size until you break it open. But anyway, you put that in the environment chamber, and then you calculate the K with F and a BEV over P. You back out a P and get a load, and then get the initial K. And then after you take it out of the chamber, you measure the final crack and assume the same displacement and back out the load from that and then the final K. So notice here, initial load is 13, initial K is 67 for the crack size of 0.8 inch. Final crack size then 1.5 inches. The load has dropped all the way down from 13 to 1, and the final K is 33. So the K did drop significantly, and then the idea here then is if you have a threshold and put it in the chamber, the crack will keep growing until you hit the threshold. So you're actually, go way back to this, actually you're coming from up here down there, and you're hoping that once you hit that, the crack stops growing. Now, in the fact that this is fairly cheap and easy to use, you could put in many specimens. Say you put in about 8 or so, and then you could take some out after 6 months, some out after 1 year. You can leave them in for a long time and see if they come up with the same number each time. And if you are used to testing, you know that when you do 2 tests, you often get 2 different answers, and you can't figure out why that didn't work the second time and worked the first time, or you don't know which one's the actual value. But testing is sometimes complicated. You don't get the same thing over and over. Anyway, this is one method for using environmentally enhanced cracking, and it's pretty handy. Another method that people used, and we used this a little bit at Westinghouse, and they use this a lot in Europe that I've seen, called rising load test. Slowly loaded rising load test in environment. So in this case, they would use a test machine. And the test machine wouldn't be so bad because you're doing it in a week or so, and not in a year. Anyway, put the specimen into the environment and test machine and load slowly. And by slowly, maybe in the order of a week of loading. So you have to have a machine that you can count on to go reliable if you're not there. Some people don't like to stay in the lab 24 hours, 5 days in a row. You get tired. So either you have somebody be in there, or you just hope that the machine works. So it loads slowly, slowly, slowly. If it's going to develop R curves like it would in air, like a K1C test, it would have then nonlinear behavior once the crack starts growing. If the environment does influence it, it would show much faster growth. So suddenly you would see this much faster growth, and you'd get a difference in load displacement curve, top one in the air, the bottom one in the bad environment, and that would indicate then that you might have then a threshold value somewhere around that point. Show you some actual data, and I'll talk a little bit more about why we did this. We did this at Westinghouse. We had a big problem with a component made of 4340 steel, so we did a lot of tests in different environments, and you can see the relative influence of the environment on crack growth rate. Here's crack growth rate, DADT. You measure DADT, not DADN, because you're not cycling. You're just holding constant load. Seawater, hydrogen gas, hydrogen sulfide gas. Air is way out here. Seawater is of interest, as I said, to the Navy and other people. At Westinghouse, we used hydrogen gas for cooling generators, and hydrogen gas makes the crack grow pretty fast. Now, hydrogen sulfide gas, people in, as I said, oil wells, gas wells, have what they call sour gas problem, which is hydrogen sulfide, and it goes really fast. You probably know that hydrogen sulfide is very toxic. It will kill you if you get into a room with hydrogen sulfide. You just drop dead pretty quickly. So the best advice is don't get into a room with hydrogen sulfide. You won't like it. The good thing about hydrogen sulfide is it smells like rotten eggs or something. It smells terrible. So if you get a very little bit, not enough to be dangerous, you know it's there, and you know get away. They said if you get a big dose of it, it smells good. But people who get a big dose of it die, so they don't really know. No, I don't know how they know when they come back from the dead and say, oh, here I was dead, but it smelled really good at the last. I don't know. Anyway, the point is seawater causes crack growth. This is inches per minute, 10 to the minus 5. A lot of times failure happens about 1 inch. So in this case, it takes about 1,000 hours to fail. In this case, takes less than 10 minutes to fail. In this case, takes less than a minute to fail. So some of these environments act very fast, and a lot of times, like this hydrogen gas and hydrogen sulfide gas, here's the threshold value, 26 and 24. they're pretty close together. The seawater is higher. One thing I wanted to point out is this is sort of a speculative thing. When you look at the effect of K, here's K versus crack growth, as you get in the lower Ks just above the threshold, the crack growth rate increases very fast. And then after a while it goes flat. It doesn't increase anymore. And people who are chemists, not my area, but chemists said the reason it doesn't go any faster is because it has reached some chemical rate limiting thing. So the idea here is you put a crack body in hydrogen gas. The hydrogen gas goes down the crack, gets reactant of the material at the crack tip, goes into the material, diffuses through the material, and then goes and does damage somewhere. One of those steps can't happen fast enough to keep this increasing. That's what the chemists are saying. So the fact that it can't happen fast enough makes this go flat. And since it goes flat, then up here, it can't grow that fast, but there's more K. You have a high K, so there's more K than you really need. So what happens is it develops multiple cracks. So one of the things about environmental cracking is you often see multiple cracks, and they call that crack branching. So you have a main crack growing, and then all of a sudden, cracks start going out from that main crack. I have it here. I didn't get it in the right thing. So here's the pre-crack. Here's the crack growing, 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 and then it hits that flat thing, so it starts branching. Almost no other fracture phenomenon makes it branch like that, and that's a consequence of the fact that you have more K than you need to grow the crack. That's what the people are saying. This is data generated by the Navy on a steel, and these people went to Key West. I don't know if you ever heard of Key West. It's a kind of a resort area in the U.S. at the very bottom of Florida. Florida, you know, is on the East Coast. It's that thing that sticks down, and the Keys stick way down almost into the tropical area, and people go there for vacations. But the Navy went there to do tests because they wanted to test in actual water. And people who did these tests had to put the specimens together in a loading apparatus, stick them in the seawater, and then sit in the beach for 6 months just watching the specimens. So it was a very hard job for them. They had to sit on the beach for six months, and but they got over it after a while. They did. Anyway, this is failure in the air. This is failure in environment, and it's a seawater environment. And this is the strength. So you can see at a certain yield strength, the K1SCC or the K1EAC goes way, way down. Goes down a little bit in air, but here it goes way, way down. This would be closer to a K1C. They didn't call it K1C because I don't know if they did actual K1C tests or whether they got a KQ or what happened, but here, this is important then in some applications causing failure, that if you get in the high strength area, you are really in a dangerous area. Look at the numbers here. Up here, about 1,000 MPAs yield strength, you have about 70. But as you get 1,500, it's down below 20. So probably down to 10. So when you have an application, you want to keep the strength low if you can help it. And this caused a problem in the initial development of things. People thought that high strength was better because all they knew about was plastic burst, yielding. They didn't want the structure to yield. And so they tried to guard against yielding by making material very high strength. And then when they made it very high strength, if it got a crack and got into environment, it had bad consequence. They grew stress corrosion cracks. And bad environment could be as thing as rainwater or humid air. Here was something, you saw how bad hydrogen was, and this was done very early on though. In pure hydrogen gas, a crack was growing. They grew the crack, and then they put a little bit of oxygen in, 0.6%, and it stopped it from growing. And then they took the environment away and put in pure hydrogen again. It grew again, put in a little bit of oxygen, it stopped it. So oxygen could stop the crack from growing, a little bit could. A lot of oxygen in hydrogen makes rocket fuel. If you get a lot of hydrogen and oxygen together and all you need is a spark, you'll blow up your lab and probably your own self too. So you don't want a lot of hydrogen and oxygen together, but this little bit seemed to be okay. If you want to find out where to get data, this is that damage tolerant handbook. They have stress corrosion cracking data. It seems to be scarcer here than it is other places. This is data from Hertzberg. Hertzberg again was one of my textbooks that I recommended. And again, Hertzberg has written more toward the material scientist than toward the mechanics person. I want to talk about corrosion fatigue, but it's about time to take the break. So the plan, we're having an extra session today, and the plan that we have is to do 15 minutes now, then have the next session and have another 15 minutes, so we don't go from the second session to the third with no break. So we'll do 15 minutes now, come back and do a session, and do 15 minutes again. We'll go an hour and then take 15 minutes again, and then have a special session. For the special session, we wanted more to generate discussion. I have some things that I put together this morning. Normally in the morning I'd go see my daughter give her lectures, but I didn't this morning. I stayed back and wrote some things to try to get discussion. But I wanted to point out one thing that I think is important, and I didn't think of it until I got a good question on it, which is how would you design using this data? Now, if you look at these values of growth, they are very fast. Once you get the crack growing, they're very fast. And if you want to do some life prediction with these, you might predict life in the order of 10 minutes, hour. If you work all day and do your calculation and say, oh, my structure is going to last for an hour, your boss isn't going to be very happy. So the only way to do is to stay below that threshold. You've got to, for whatever it is, stay below the threshold or try to have no defect whatsoever. Now, a lot of times people assume there's no defect, but it's difficult to really guarantee that there's no defect. So the other thing, avoid the environment if you can. Avoid the yield strength range where you have trouble. Here you have high yield strength, bad trouble, lower yield strength is not so bad. I want to talk a little bit about fatigue. Fatigue in environment is pretty much different from fatigue in air in that the environment causes things to happen that aren't very good. So a combination of fatigue loading and an aggressive environment we call corrosion fatigue. The environment accelerates the crack growth over just air conditions, non-corrosive. And more susceptible materials seem to have faster crack growth. Slower frequency seems to have faster crack growth. Here's just an example of an unknown steel. A lot of times people don't want you to know what material they have, so they give it some letter or something. But here it was tested in air, and then the trend line, d/ADN delta K line, was written in air. So it had a power law, like a Paris law. Here it was done in sodium chloride environment. That's again a seawater type environment, and it is trend line is 5 times faster. It's a parallel, but it's just 5 times faster if you look at the coefficient here. 1.25 10 to the minus 8 versus 2.5 10 to the minus 9. So that's influence. Now, here was seawater and 4340 steel. And if you go back, look at this. Seawater and 4340 steel, low strength, not so susceptible, high strength is susceptible, and it happened that way in corrosion fatigue. So here is 2 strength levels, 130 and 180. They happen to be KSI, but in air they both had the same trend line, so there was no difference. In seawater, the lower strength was about 2 to 3 times faster. The higher strength was about 10 times faster. So the higher strength really was more susceptible to corrosion fatigue problems than the lower strength. Here again is a steel. This is a different one, 12 nickel. I think that would be what we call ferritic stainless, something like that, real high alloy steel. Anyway, it was tested in air and then in the seawater environment at 3 frequencies. So 600 cycles per minute would be 10 hertz. 10 cycles per minute, or 60, I think that 60, that didn't come through good, be 1 hertz. And then 6.1 hertz. Now the slower you go, the more susceptible it is. And it's a very logical explanation of why slow frequency is worse, because you are loading into a susceptible range, the crack starts to have environmental effect, and then you come back out of it again. So every cycle you load into an environmental range, and then you come out of it. And then if you do a fast frequency, you're up and down, and you don't spend much time in any one cycle in that bad range. If you have a slow frequency, you're up there for quite a while. So 6 cycles per minute, you're up there 10 seconds, then 10 seconds in that range, and then you get that big effect. Here's some HY80 and HY130 in air. Now this is higher strength than that one. They didn't line up the right way. I don't know what was the matter with them, but they didn't do it. This is a steel that the U.S. Navy like to use for submarines. So it's a submarine steel. I want to show you that. So that's corrosion fatigue. Now, the thing should have pointed out while you saw the pictures is that corrosion fatigue in a bad environment is very particular to the conditions. It depends on the environment, the material, the frequency you test, and it's very difficult to test in one thing and say I'm going to apply that to another condition. You can't test one condition and say that has applications in a variety of areas, but it doesn't. You almost have to test your exact condition if you want to use that data. So you have to get the right material, the right environment, the right frequency of loading, or don't build anything that goes in environment. That's bad stuff. Questions on this? This was short, but I just wanted to show you a little bit about that. This is a fairly important section for a couple reasons. One is you learned all about fracture mechanics. One, the parameters, how things behave fracture toughness under monotonic loading, how things behave, fatigue loading, and how things behave in environment. And then the next logical step is applying that to structures. So one, it's important to learn how to apply this to structures. Two, I'm going to give you a little quiz next week, and it features a lot of this section. So I hope that by next week you can get this downloaded. Those of you who download it, you don't have anything more than the first lecture, is that right? Yeah, I hope that you get this by the next week, or else we'll have to put it up here. So maybe you should take notes or pay attention here. As I said, this is fairly important. Here is a little bit of background on applications. We do applications for a structure to set design criteria. Design criteria would be how big do you make the material, or the structure, what size of this and that, and maybe how much load can it stand. And then secondly, maybe not second, but along with that is material selection. If you know what stresses you have to sustain in your structure, you help you make material. You want to avoid yielding, of course, and that's not the only thing. In the olden days, people just tried to avoid yielding, and they didn't know about fracture mechanics. However, in most cases, if you try to avoid yielding by making the material stronger and stronger, then you run into problems with fracture, stress corrosion, cracking, all kinds of things. So it's not always good, the material selection. You have to make some compromises, high enough to avoid yielding, low enough to avoid fracture problems. Now, as I told you before, if you don't do a good job on these, you will end up maybe doing this, called failure analysis, which is, in the U.S., is a big business. I don't know if you have a lot of failure analysis people here. You can, once you do that, you can make a lot of money as a private consultant. Anytime something breaks, you run to it and you tell them you're going to tell how to fix it. Kind of like lawyers. I don't know if you have lawyers here. We have lawyers that chase accidents, we say. Every time an accident, here's a lawyer. Oh, hire me and I'm going to get you a lot of money for this accident. So same thing with failure analysis. Hire me and I'll tell you why your thing failed. We use fracture mechanics in the linear elastic range to do the analysis with the three things in mind that come into fracture mechanics analysis, which are the stresses, the defect sizes, and the material properties. Normally when you're doing an analysis, if you know two corners, you predict the third. So that's how the analysis is often done. Know two corners, predict the third corner. A lot of times the corner you want to predict is defect size, because you can do life calculation that way. If you know the defect size pre-existing, say, you can do then crack growth rate analysis to find out when it'll fail. Final failure happens when you get to K1C. Sometimes you can do crack initiation, and the things we talked about yesterday, like stress life, strain life, low cycle fatigue, high cycle fatigue, they all can be used for crack initiation. Now, it was a topic that people talked about. When do you go from stress life to saying I actually have a crack that have to do? So that's a difficult topic, but won't do that right away. I want to do some calculations for you to show you how to apply things in a simple manner. So given a wide plate with a central crack, by a wide plate we're meaning then that it is a Griffiths geometry and has infinite width, almost infinite width. I'm going to use K1C from that one problem we did, I guess it was Tuesday maybe, We did that one problem, K1C, and got 81 KSI root inch. I'm doing this in engineering units. So given 2A here is 3 inches, what's critical stress for failure assuming infinite plate? So 2A is 3 inches, 1A is 1.5. Now here is the center crack specimen calibration. Infinite plate is a mechanics way of saying that A over B, the crack to width, goes towards 0. When that goes towards 0, the capital F here is 1. And we do a lot of calculations with that being 1 because it just is convenient. So then sigma squared root of pi a, capital F is 1. You don't usually write a 1 here. So you can set up the calculation like this. K1C is 81, stress is unknown, square root of pi times a is 1.5. Calculate the stress from that, 37.3. More often we do it this way. Say given the stress is 25, what's the critical defect size? So 81 is 25, square root of pi a, and calculate A is 3.34. So 2A, which is the total defect, 2A would be 6.68. Mostly you don't have infinite plates. So when you have finite plates, you have to do a little bit more calculation, and you need to use this table or this chart. You have this in your handout. At least you should be in the handout. Now, okay, a finite plate, 2B or W is 10 inches, thickness is 1, stress is 25, so load would be 250. Again, we calculate stresses without a defect in there. So the stress calculation that goes in sigma square root of pi a is without a defect. So what's critical crack size? Now when you write K, here you have square root of pi a is crack size, and then F is a function of A over B. It means a function of A over B. So in this analysis, then you have A here and A there. So you can't solve for A directly because it's at 2 places. And in one case, the A is embedded in this graph or this table, and in the other case, it's under the radical. So there's really no way to calculate A directly. So you do it indirectly. We call it trial and error, iteration, a lot of different words. It means you have to take several steps and try to figure out what that A is. So in the steps, start with a guess. What if A is 3.34? Then A over B is 0.67. Go back to here, 0.67 is down here. I told you it was okay to do a linear interpolation, and my linear interpolation said that F would be about 1.42. So now all you can do is calculate K from these data, and I got 115. Now the failure K that we picked was 81. So 115K is too big. And then the next step is to back off a little bit and try another one. And just keep trying and trying until you get a good number. So I picked 2.5. 2.5 A over B is 0.5. 0.5, 1.187 here is pretty easy to find that. K was 83.2. It's close, but it's still a little bit too high. So I backed off a little bit. A is 2.4. I have to interpolate to get the F, and I got 80.9. So 80.9 is good enough. You could keep trying until you get exactly, but that's good enough. So A critical is 2.4. The defect size, again, which is 2A, would be twice that, 4.8. So that's one skill that you should know how to do. Given data on K1C and loading and so forth, can you get critical crack size? That comes up a lot. And especially in fatigue life, you need to know critical crack size. Now, the second thing, once you know how to get critical crack size, is how can you calculate fatigue life? And we're going to do it using the Paris law. The other laws that I showed you yesterday are too complicated to use. So you have, again, the algorithm. K is sigma squared of pi a capital F. Then d/ADN, put delta K in there in terms of delta sigma, square root of pi a capital F to the n, and then separate them out and integrate the left side. If you go from 0 to cycles to fail, then that's cycles to fail. The right side goes from initial crack size to a final crack size. All the rest of this stuff is over there. Now, initial crack size, usually you have to pick a value. And the way it's often picked is to talk to non-destructive evaluation people and saying, if you were going to study or look at the structure with your non-destructive tools, how big a defect could you miss? Not how big can you find, but what might you miss? And non-destructive evaluation uses things like X-rays, ultrasonics, surface, dye surface, all kinds of stuff. Anyway, this is that. Then the A final should come from K1C calculation, just like we did here. A K1C calculation would do it. So this is a lot easier if you don't have to vary F, if you just keep F constant. So I'm going to try that with a constant F. And to do that, I'm going to use a central crack of a very wide plate, load it from 0 to 25, and pick 0.1 inch for the initial crack size. Now the final crack size, K1C, in my plate, I picked from this calculation that we just did here. So I didn't want to do it over again. So we picked that, 3.34, and the crack growth rate law, I just picked out of the air. Now how many cycles to fail does that predict? So delta K is delta sigma square root of pi a. In doing the fatigue calculation, the delta sigma is the maximum minus the minimum. But notice if you're going to do K1C, if the minimum is not 0, you have to have a range that's between maximum and minimum, but you have to calculate K1C at the maximum load. We're assuming that you load up, down, up, down, up, down, and suddenly when you come to maximum load, bang, you get K1C and things fail. So the range then is going to be 25. This is the crack growth rate law, 1.1 times 10 to the minus 9. 25 is here, square root of pi a to the cubed. All the parameters are known here but the crack size. The crack size is a variable that goes into this. So you take all these numbers, 25 times square root of pi, cube it, take that value times the coefficient out front, and get a number here. Was 8.70 times 10 to the minus 5. Now square root of a to the cubed, of course, is a to the 3/2 power. And then when you rearrange it, dn on one side, dA over all this on the other side. This integrates like x to the n. If you know x to the n, you integrate to x to the n plus 1 over n plus 1. So you're going to say then when you integrate this, if you bring the a up here, it's a to the minus 3/2 power up here. So this coefficient can come outside. It doesn't impact the integration. So you're integrating a to the minus 3/2 dA. So you integrate that, you raise the exponent by 1. It raises from minus 3/2 to minus 1/2, and then you divide by the exponent, the new exponent, minus 1/2. So this is the integration. Now, definite integral, you have to evaluate at the bottom limit and the top limit. So with a minus sign in here, the bottom limit is a minus sign, with a minus minus becomes plus. The top limit is a plus sign with a minus here, becomes minus. So then you're evaluating, bring the 2 up here, over 8.7 times 10 to the minus 5, 1 over square root of 0.1, minus 1 over square root of 3.34, you get a number, 60,000. So 60,000. So the D80N delta K method allows you to get quantitative values. The fracture mechanics method is all quantitative. You get quantitative final crack size, you get quantitative fatigue lives. In general, you can have fatigue laws and limits and things here and get numbers up to about 1 million cycles, depending on the condition. You can never get fatigue crack growth rate that gives you 1 billion cycles. So 10 to the 9 cycles. You never have a condition that would do that. So if you get into really high cycle applications, billions of cycles in the life, you have to rely on the threshold, and you can't rely on just this method. But for things that have cyclic life in the thousands to 1 million, it works pretty good. A lot of stuff like, say, the airplane. The major cycle on an airplane has the wings kind of download, and then the airplane takes off and the wings raise like that, and they get a big load on the wings, and that's the major load on the aircraft, and then it lands again and the wings go back down. So every time a plane takes off and lands, it gets one big fatigue cycle. And if the people want to do that analysis, 60,000 takeoff landings is pretty many. So that's not bad. If you do this analysis and get a number, I wouldn't rely on it exactly to the number. I'd say if you're predicting a life of about 60,000 cycles, maybe it's good for 6 to 10,000, and then you might want to do it over again, do inspection or something. Now, I don't know if you've had this. This is one case. I have a K1C, initial crack size, a fatigue crack law, and a stress. We used to get this problem. Somebody would say, we are worried about fatigue failure, but we don't know what the material we have is. We don't know if there's a crack in it or not. We don't know what the loads on that structure is. Can you make an analysis for us? So you have no loads, no material, no anything, and you're supposed to make an analysis. So this is what you can do. Take these numbers and change them systematically, and then generate these kind of parametric curves, to call them, for different initial crack sizes, different stresses. You can predict cycles to fail. Maybe you do 10 values for each curve. And after you predict all that, you can plot that up and give it to the person who wants to know what life is, and tell them when you figure out what you have, then you can use this. And I can't do anything more if you don't know what anything is. Didn't want to do that. I want to talk about some special application methods in fracture mechanics. One's called leak before break and one's called proof testing. Let me start with proof testing because that's quicker. Proof testing is used in pressure vessels and pipes, anything that contains pressure, and what people do is load to a stress higher than operating and see if there's no failure. If there's no failure, you can then assume that you are about to fail and get an initial crack size from the K1C value. Proof testing does a couple things. It overloads the crack. Remember the data we showed yesterday? When you overload a crack, you change the closure and it raises the life. You get an enhanced life by overloading, but you can't quantify it. You don't know exactly how much more life you get. You just know you get more life. So some people think that then doing proof tests can improve the life of their structure and can tell that there's no failure. And sometimes you do damage, though. So sometimes proof testing is worse than nothing, but people do it a lot. Now, proof testing story that helped fracture mechanics come up at least at Westinghouse and in power generation and in the Navy besides. A long time ago, the U.S. Navy was building nuclear-powered submarines. So they had many nuclear-powered submarines, and there was an admiral in charge of this called Admiral Rickover, who was quite a tyrant, and every time somebody saw him, they got so nervous they almost fainted away, because if he didn't like you, he would fire you and say, you're out of a job. So nobody wanted to see him. Anyway, but he did develop this nuclear navy, and one of the parts of Westinghouse was in charge of doing the analysis for this and looking at it. And what happened then is they had containment vessels for this nuclear reactor, because of course you don't want to be in a submarine with nuclear things leaking. They did proof testing, and one time they did a proof test that burst the vessel. So that wasn't good. Number one, the vessel burst. Number two, the vessel burst at a pressure lower than operating pressure. They already had many submarines out there operating with the pressure up here, and the thing burst down here. And then, of course, that gets people excited. So everybody got nervous. What's the matter? Are we going to burst all our vessels? Burst a vessel in a submarine, you get all that stuff inside the submarine. That's not good. People would probably all die inside there. Anyway, the person who was to be my boss at Westinghouse had just learned fracture mechanics and was getting into it. So he went and told them, number one, we got to take that material and get K1C. Number two, you got to take all the vessels that you have and do an inspection to see if there's any defects. If there's defects, then you have to say, is K greater than K1C under the operating pressure or not? And if it's not, then this one case was just, you know, a fluke. It wasn't typical of what might happen. So they started doing that. K1C testing and then inspection, and they found that they didn't have cracks, and nothing more happened. There was never another accident. So after they did that fracture mechanics analysis and sort of saved everybody from being embarrassed by an accident, fracture mechanics got more importance. Said, oh look, it works pretty good, doesn't it? And then power generation has used that for a long time. So in the U.S., the power generation of Westinghouse and General Electric and all those companies that do power generation. So that came from proof testing. Another method is called leak before break, and this again is for pressure containing things. And this is kind of not real quantitative, but somewhat. And as I said, you usually in a structure have a surface flaw like this. Here's the wall of a pipe or a pressure vessel. It's hard to see, but this is, say you cut the pipe and you look at the cut part, and here's a flaw on the inside. So that's a flaw. Now, for that flaw, you assume that it should grow in a certain way, and then when it grows far enough, it'll get to the outside of the wall. So this would be the inside, where you might have something maybe not bad, maybe water, air pressure, something like that. And then as the crack grows, it gets a new shape, and then when it gets all the way through, whatever's inside can start leaking out. And when it starts leaking out, then you can say, oh, crack has gotten all the way through, we better shut down this particular thing because it's leaking whatever's inside, and we don't want to have that operate anymore. But the danger then is before it leaks, it could burst. So once it gets to the point where it would leak through, and you have to assume some section here, you would pick a final crack size and use then a K1C with a center crack. You assume that this is a big crack here, and then do K1C analysis and see if this crack has reached K1C given the internal pressure and the size of the crack or not. If it has reached K1C by this time, it's going to burst before it leaks. And if it hasn't reached K1C, it'll leak before it bursts. So this is called leak before break. You have to decide whether you're going to leak or whether you're going to break first. So you assume the surface flow grows, then when it gets through, take that size as the crack size and see if that would burst. Now, you remember the part through calculations we did way back, I guess Monday, and we were saying how the K varies around the crack because 90 degrees, sine is 1, cosine is 0, so 90 degrees you get a 1 here, but 0 degrees you get a 1 there. And so this is smaller generally because A over C is less than 1. This is smaller. And so if you have 0 degrees, you have a low K, and 90 degrees, you get a high K. Let me show you calculations for that in case you want to calculate part through cracks. So I'm going to have A be 1, 2C here. A is 1, 2C is 6, stress is 30. A over 2C is 0.167. A over C would be 0.333. So this is the Q factor that goes down here, and then it has 1.122 out front. Stress is 30. All this gives 56 times that. So again, K is a function of position, and at 90 degrees, K then comes out to be 56.3. That's the deepest part of the crack. At 0 degrees, K comes out to be 32.5, almost half of that value. So as a consequence, when you have a long, narrow crack under pure tension, K is much higher here than it is there. If you have a fatigue situation, the crack wants to grow faster here than it does here. And if it grows faster here, eventually you get to the point where this is 1, semicircular crack. And when that's 1, then you have sine squared plus cosine squared, which all you know from trigonometry is an identity. Sine squared plus cosine squared equals 1. So this whole thing goes to 1, and all you have left is this stuff out front. So as a consequence, given pure tension without anything to interrupt, the crack wants to grow into a semicircle. So if it's long and thin to start with, it tries to grow into a semicircle. So that gives you some idea of how to assume the shape of the crack as it grows. Some of the ways that things are being used is in ASM boiler and pressure vessel code. They use fracture mechanics in several things, mostly related to nuclear power plants. Section 3, Appendix G uses it. Section 11 uses it in this way. I don't know if you use any ASME codes here. ASME codes are written so that nobody can understand them, just like ASTM standards. These things are a big mess. If anybody learns to read them and understand them, you can act as a consultant and tell other people what they mean, because normal people can't read them and understand them. Have you tried? Big mess. Yeah. I don't know why that is. I think it's because people want to have exclusively access to that for themselves. So the people who write them so that nobody else can understand them. And if somebody wants to know what they say, they say, oh, you got to go to the people who wrote them, which is me. And if you're going to come to me to find out what they say, you have to pay me a lot of money. So that's that. The two things, one is fracture mechanics. K1C and K1R curves are part of this thing, that section 3 and also section 11. And they look like this. Here's a bunch of data. We talked about K1C testing on Tuesday, Wednesday. No, today's Thursday, isn't it? It's hard to keep track of days when you're having so much fun as this. Anyway, K1C. Then we talked about doing rapid load test. And these were rapid load tests done in the old days. K1 dynamic, it means. They have a new nomenclature for that. But back then it didn't. And then crack arrest tests, those messy tests, crack arrest. They took all these data. All the K1C are open circles. They tried to take a line that went under all the open circles. Then the other data, altogether, they tried to take a line that went under everything. They fitted those lines with an exponential curve. And that exponential curve was one for K1C, one for K1R. K1R stands for K1 reference, so it just means K1 reference. And those are the curves then that they used for their data, the lower bound. One of the bad things about these are that the abscissa here, the horizontal ordinate here, is a temperature that is not based on fracture mechanics, but based on NDT. I don't know if any of you ever tried NDT testing. What they do in NDT testing is have a specimen with a weld defect, and they set it somewhere, and they have a huge machine with a weight high up in the air, and they drop it down, and it comes down and whacks the poor specimen, and then they see if the specimen cracked or not. And the point between cracking and not cracking is called NDT. And that's not really a fracture mechanics test, but they get a temperature. They do it at a grade of temperatures, and every grade of temperature they let it whack, and they say, oh, okay, when, it broke. No, it didn't break. And I think the last break is the NDT. Anyway, that's those curves. And they're still used in ASME boiler pressure vessel codes. The other thing that was used is fatigue, and I told you here they're using it down here in section 11. Section 3 is construction rules. Section 11 is inspection rules. So they used that for inspection. And one of the things they had trouble with is in boiling water reactors, they got bad environmental effects from the chemistry of the boiling water, corrosion fatigue type of thing that we just studied earlier. So here is data, low R ratio, high R ratio, D80N, delta K. You can't read these very well, but this is D80N, that's delta K. You can see the trend lines. Unfortunately, I don't have them on top of each other, but this is what the data looks like, low R ratio, high R ratio in the bad environment. So this is an environment. To give you an idea of the difference, delta K here of 10, come up here, D80N is about, this is 10 to the minus 6, 10 to the minus 5. I had a copy of that from somewhere and it wasn't very good. But anyway, D80N at 10 is about 10 to the minus 5 here. And back here, D80N delta K about 10 is below 10 to the minus 6. So that environment increased crack growth rate more than a factor of 10. So it is really bad. And they use these. I guess they work pretty good. I'm not real familiar with them, but I think they work pretty good. So that's the end of application section. I hope you can get a copy of that, because that's important to learn how to apply things. This is just linear elastic applications. There are other application methods that come about. Questions on these applications at all? I think we'll maybe do this more tomorrow, but let me
Talk in a little bit, then we'll take a break. I just want to go over this one just briefly. Here are the data to start, and don't have the displacement here was 0.012. I didn't get it on there. But anyway, you have to use your table, and the reason the table is so important that everything we do comes off of that table in terms of linear elastic fracture behavior. So BEV over P and F, you have to back out the P for the initial condition, 9.73, and then the initial K value was 66.5. Then final crack size 1.5 inches. You do the same thing. Get A over W now is 0.75, so you have to go back to the table, get the VEV over P and the F value, and back out the load 1.94, and get then K is 39.6. Notice the load drops considerably. The K drops by almost a factor of 2, not quite. So if you were doing the bolt load test, you would assume then that that is the K1 SCC. If you weren't sure about that, you could do several tests, some shorter, some longer, some duplicates, but that's, that's that one. Now, I think we should take 15 minutes of break again. That was suggested, and then we'll go. I have a special session that is not exactly lecture, but maybe help discussion and centering on some of the issues that I got questions about. Okay, this is the time we said we would start again. Now, this third session of the day was labeled as discussion and self-study, and I didn't know what that meant exactly. So what I have is generated some things for you to look at that might generate discussion. So either this will help generate discussion and we'll have discussion, or it won't. If it doesn't generate discussion, we won't have discussion. It's very simple. Now, some of the questions I heard through the week are in this, and this, I didn't come prepared with this. I just made this up this morning. So can look at this. I want to talk about mixed mode, mode 2 and mixed mode, and composite materials. That was some of the questions that came up. Now let me review again. In the loading of a crack, we had 3 modes. One was mode 1, which we've done everything so far. Opening mode, all the loads are perpendicular to the crack, all the stresses are. All the mode 2 is in plane shear, all the loads are parallel to the crack, but in the plane. And mode 3 is out of plane shear, all the loads are parallel to the crack, but out of the plane. Now, mode 3 isn't very popular. I don't know if there's no failures for that. The reason that comes up sometimes, I don't know if any of you are work in theory of elasticity or whatever, mode 1 and mode 2 are kind of plain stress problems. When you do the theory of elasticity, you get a fourth order equation that nobody can solve very easily. In mode 3, you get a second order equation. You essentially get Laplace's equation. So the Laplace's equation people have been able to solve from time to time. So people in the old days, at least, used to do mode 3 problems because they could do it. It was easy to do. So if you wanted to do something you could do a mode 3, mode 1 and mode 2. Sometimes they said then by analogy they should do whatever. Anyway, I want to then go from mode 1 to mode 2 and combine modes a little bit. Here's the problem with mode 2. The crack tip stress field distribution from mode 1 to mode 2 are not similar. Show you here, this is the y direction stress. So the y direction stress, you had this in the second lecture, and it has this distribution that I told you is a unique distribution, so that any mode 1 loading that has a crack always has the same distribution, and the only parameter you have to worry about is K1. The K, the crack tip stress intensity factor, we called it from George Irwin. Now the mode 2 loading has a different distribution function, still has square root of 2 pi r in the denominator, but these things are all different. And so from here to here, I think they should be times. Yeah, well, no, they're times. From here to here, you just can't then add the two stresses together. You can't add K1 and K2 because you have different distributions. You don't get an aggregate K. The only way to do them is combined with the Griffiths G. The reason being then, the total K due to mode 1 and mode 2 loading together is not working. It's not valid. So the fields need to be combined with a scalar term. In this case, the Griffiths energy is a scalar term. Stresses are second order tensors, as some of you may know. Second order tensors are one step beyond vectors, kind of. So you then, for the case of combined loading, you have a problem because you can't add K's, you have to add the G's. The conversion from K to G is this. There are two elastic constants, the E elastic modulus and the nu is called Poisson ratio. So the K1 converts to Griffiths G like that. The K2 converts to Griffiths G like this. So to get a Griffiths G that is combined in both fields, you have to add the K's together and get, this is a scalar term then, no longer a vector term. So this combines the field in an adequate way. Now, if you want to apply this to a mixed mode problem, here's a mixed mode problem. Say you have loading and a slanted crack that's slanted at an angle theta, still 2A, but then the load is not entirely perpendicular to the crack or entirely parallel to the crack. It's in between. So what you must do then is use kind of a stress transformation formulas. I don't know if you know the Mohr circle. We use Mohr circle in mechanics of materials, and kind of a Mohr circle analysis, and you get the K1 mode and the K2 mode, and that would be then the K1 mode would be the component here perpendicular, and K2 would be the parallel component. So those two components are K. Now remember that the combined K1 and K2, just adding them together, doesn't make sense here. You have to go through the Griffiths G. Normally you use the 1 minus nu squared for plane strain. I didn't have it in this slide. This is for plane stress, but it's similar. The 1 minus nu squared is a fairly small term, only about 5% in general. Now, if you want to do fracture toughness, there is a problem in that people have done a lot of K1C measurements. K1C is often measured. K2C is not often measured. People try to make K2 tests, and they've done that successfully, but not many people do it. I know of about 2 or 3 labs that worked on doing K2 tests, and just, I don't know, just didn't seem to work real good. If you do K2 tests, they usually got a higher value of K2C than K1C. So the failure then would come about as a locus, K1C, K2C. If K2C and K1C are equal, this locus wasn't drawn very well, but that locus should be a semicircle. So if K1 and K2C are the same, it should be a semicircle, or a quarter circle, I guess you'd call it. The circle failure locus could be conservative. So when in doubt, you can measure K2C and use an elliptical failure line. So you can make this be an ellipse and not a semicircle. But you have to go through that mess to do the analysis for mode 2 loading or anything like that. The mode 2 specimens people used, trouble is if you say just have a pure mode 2 and you load like that, you get an unbalanced moment, you get funny moments. So you have to people make a 2-crack specimen and they pull the middle and pull the outsides or whatever. So that's it for mode 1, mode 2 loading. Does that generate any discussion or interest? Nothing? Okay, as I said, if it doesn't generate discussion, it doesn't. We won't discuss it. Now, the other thing I want to talk a little bit about is composite materials. And composite materials, somewhat related to the thing that I just discussed, because they have mode 1, mode 2 problems. Now, I never worked in composite materials myself. I worked in polymers, but polymers are isotropic. So composite materials, I just look at what I could find in that. So they are not homogeneous and isotropic. The basic assumption of the K development through theory of elasticity is a homogeneous isotropic material. When you have that, the K versus G conversion you make with only 2 constants. Oops, that's the wrong way. The 2 constants are E and nu, and then the third constant is not independent. Anyway, composite materials may be orthotropic. Now, say a little bit of that. When a material isn't isotropic, it's usually labeled as anisotropic. Isotropic material have 3 constants, E, G, and nu. We call that elastic modulus, shear modulus, Poisson ratio. G is not independent, though. It's dependent on E and nu, like that. So there's only 2 independent constants. Now, anisotropic and orthotropic material, generally anisotropic materials may have up to 21 elastic constants. So 21 elastic constants versus 2 makes a big mess when you're trying to go Ks and all that kind of stuff. However, orthotropic materials are materials that have properties that differ along 3 mutually perpendicular axes and have axes of rotational symmetry. So orthotropic materials usually limit themselves to only 9 elastic constants. And they are the E in 3 directions, E in X, E in Y, E in Z. We use X, Y, and Z as our axes, 3-dimensional axes. And then they have 3 Poisson ratios and 3 shear modulus. So these 3, and I'm not sure how they fit together, whether there's some dependency among them, but usually people represent them in a matrix, and they are then much bigger mess than isotropic materials. So if you have a line reinforcement, like fibers or whatever that in the composite materials that are aligned, then the material could be isotropic. And in this case, then the K doesn't work so good because you don't have E the same in every direction. Now, as you know, a material assumed to be isotropic and homogeneous is not truly so, but we assume it's so if it's within a few percent of being that. And the reason you assume it's so is because it's so much easier to do the arithmetic than with the orthotropic material. So the development of G can contain many elastic constants, and I don't know them all. Here are some of the problems you would run into with fracture in composite materials. Crack doesn't always seem to grow straight ahead, but sometimes at an angle. So if you start with a crack growing mode 1, maybe it shoots off into mode 1 and mode 2. The reason I did that mode 1, mode 2 analysis is to show you what you're up against, but that was with isotropic material. In this case, you have orthotropic material, mode 1, mode 2 analysis. A lot of times they say then delamination is more of a problem than plain old fracture. And many of the studies might require numerical techniques to get through that. Here's some examples of where you can find stuff, and if you want to know a lot about this, you mostly have to look up fracture mechanics work for composite materials. You can find them in conferences, literature and journal, or on the internet. I don't know much about the literature. Generally, when I get papers to review or go to conferences with fracture, we have just regular isotropic material, so I don't see much on that. But you can also find stuff on the internet. The trouble with on the internet is you see a title and an abstract, and if you like it, you probably have to pay to get it. If you don't feel like paying, tough luck, you don't get it. Let me talk about conferences. Here's one place that I found things coming up. So the interest in composite materials has not gone away. There's a conference called International Conference on Fracture. It's a fairly old conference and is the most important worldwide conference on fracture. It started in Japan and has been held all over the world. I don't know about South America and Africa, but Europe, US, Asia, Australia. An example is it was in New Delhi in 1984. It's not held often. It started in 1960s maybe, and it's held at most every 4 years. So that conference is held frequently, or not frequently, but about every 4 years. Now, the next conference is ICF 14. 14th International Conference on Fracture is in Rhodes, Greece during these dates, 2017. I looked up this, well, I get emails from the guy, I can't say his name because he's Greek, Godos something. I don't know if you know him, I don't know him, but he sends messages to everybody in the world that he finds on the internet and asks for special sessions. As a result, he has more than 60 special sessions. And I don't know if you go to conferences much, but when you go to these big conferences, like this thing, 5 days, say, or maybe 5.5, you have opening ceremonies, plenary lectures where the more important people give lectures, closing ceremonies. So that leaves about 3 days for special sessions. When you have 3 days for special sessions, say you have one session in the morning, one special session in the afternoon. Sometimes they put a session at night, but everybody's so tired by then, they don't go anyway. So one session in the morning, one session in the afternoon, 6 times for sessions, for 60 sessions. As a result, you usually have 10 simultaneous sessions, and 10 simultaneous sessions, nobody goes to anything. They're just overwhelmed. You know, I wanted to go to 1, 2, 3, and I can't go to all 3 at once, so I just skip it all. And especially maybe in Greece, they want to go out touring instead. So as a result, with so many sessions, usually you get the authors and maybe about 2 or 3 people interested. You get about 6 or 8 people, and that's a shame to do all that work on a paper, travel from wherever to Greece, and then give a paper with about a half a dozen people listening. Anyway, that wasn't the point. The point is I wanted to show you that 2 of the sessions are related to composite materials. They're sessions on everything. Nanomaterials. I know some people here work on numerical methods. I have them listed for talk about them a little bit more next week. But fatigue, fracture, structural integrity, and so forth for polymer composites and adhesives. So that's more generic. These are the 2 guys that generated that session. Fatigue of composites and adhesive by this fella. So he has 2 sessions. In this case, he has some collaborators. Means he probably got these guys to give papers in his session. Maybe here he has to do them by himself. Anyway, polymer composites, but also adhesives. So adhesives have maybe some of the same problems of delamination and that kind of stuff. Here are some papers I found on the internet, and as I said, they look interesting, but you can't get them usually unless you pay money. One of the big things, computational fracture mechanics for composites, and this came from NASA. Well, related to NASA, National Institute of Aerospace in Hampton, Virginia. Hampton, Virginia is the one headquarters for NASA, the U.S. NASA, and all these government things have people who are kind of consulting people that do work for the government, but don't get paid directly by the government, but indirectly. So, computational fracture mechanics. Some of these are pretty old, 20, 30 years old. Fracture mechanics for delamination. I told you that delamination is a problem. This guy, used to know him a long time ago, but I forgot who he is. I think he was a guy that worked so hard he sleeps in his office. The Department of Theoretical and Applied Mechanics at University of Illinois has been dismantled and put into the Mechanical Engineering Department now, so there is no such thing. So this is fairly old. And then here is one, University of Utah, fracture testing. This is more of interest to me that they do fracture testing for composites. Sometimes I think they test them and ignore the problems of orthotropic behavior and all those constants. They just come up with them. As I said, I hadn't worked in this area, nor have I read those papers because of you can't get them unless you pay money. And as you know, we can't pay anything anymore in India for a while unless you pay 100 rupees at a time. I think that was all I had on. No, this is just information, I guess. I had this, and I wondered if there's more discussion on any of these areas. So, any discussion or thing about either mixed mode or composite materials? You have? Uh-huh. when you do the fatigue, do you get a crack to grow, or you get delamination of? Yeah. Uh-huh. And you use, yeah. And you use G. Yeah, I think exclusively, because the K doesn't make much sense for, yeah. Is there a committee on composites? Do you know in ASTM? What's the What's the title of the standard? Is it an E standard or another D? Okay. Yeah. The ASTM standards I've showed you so far are all E. E is kind of mechanical testing of homogeneous materials. I think polymers is D. It's yeah. Maybe you're not interested, but discussion. The polymer people have written K1C standards. That's a D standard, and they sort of followed the E399, but not completely, because there are other problems. As you know, you get time dependency, kind of viscoelastic behavior in some polymers. And if you test at different rates, you should get different things. Have you tested polymer materials? I was doing some polymer testing for a Biomedical company. They make polymer implant stuff. And I did it some years ago, not knowing that I would be a recipient. I had an implant about 3 years ago. They put a new hip in, so it has metal, but mostly titanium, cobalt, and then there's polymer for the, what do you call that, friction, for the friction wear. And it should be good until it wears out or I die, one of the two. They're hoping that I die before it wears out, but I wasn't looking forward to dying anytime soon. So, yeah, but anyway, some years ago for this company called Zimmer in the United States, they make a lot of polymer implant materials, and I did the testing for them. But I used the nonlinear fracture mechanics approaches that we'll learn about next week. Do you have composite companies, polymer companies here? Your biomedical industry? They're not. You have a lot of implants done in hospitals here. Do you have what's called the medical tourism, where people from other countries come, and because medical procedures in the United States are so expensive, and they like to go somewhere else where it's cheaper, but then you go maybe do a tour and then you get your implant. So you should do your tour first, because after you get the implant you can't walk for a while. Is what? I don't count on it. Oh. people in the United States who've never been anywhere and don't know what's going on in the world think that we have the best, cheapest medical care in the whole world, and it's just opposite. It's one of the worst medical plans and most expensive. The quality of the doctors is okay. The doctors are okay. It's insurance companies and pharmaceuticals. I don't know if you have that problem here. Most countries don't. Some of our pharmaceutical companies raise prices so high nobody can afford. They either they don't get them through insurance. They have to pay out of their pocket. They go bankrupt or whatever over their medical problems. So where do you do the testing? Here on this place, or your composite testing here? Do you say you get a big mess sometimes and you don't? Oh, you do G1C test. Do you do it composite? Do you do it in several directions? Okay. So you don't never do it in the along, just you just do it perpendicular to fibers, and then the different things delaminate. How would 3-point bending? Oh, okay. Yeah. You never do mode 3, I guess. Nobody's interested in that anyway. So when you do 3-point bending, you get mode 1 and mode 2 together, or just mode 2? Yeah. Is that have a crack then along? Okay. So here's your bend bar. The crack goes this way, and then you load bending this way. So you get the beam shear that we teach in mechanics of materials. Students used to hate that. I don't know what letters we use. We had V, shear load, Q was that funny factor, and then moment I and T, moment of inertia, I and T thickness. So VQ over IT, and students never get it. And I was to tell them the reason we try to teach that is to torture you. So do you normally publish your works? You normally publish a lot in international journals, fracture journals, or composite journals. Yeah. Do you do anything on test technique then? Publish? Because that might be valuable, because if somebody goes to do a test, they don't know sometimes where to start. So a paper on test technique could be valuable. You get more points if you publish a lot than if you don't publish a lot. So same everywhere. I think it's probably not worth to start anything new, because this was supposed to be discussion. I'd like to discuss more, but if you don't have anything more to discuss, we won't. You have anything? I think we won't. Tomorrow, I want to start out. We did one problem in applications. I want to do some problems in applications. That session I had on applications, I want to have you do actual yourself. Try some of those things because it's a help if you can do that. And I have also for tomorrow some case study sort of things besides that application. And then next week, I'm going to start on nonlinear fracture mechanics. Nonlinear fracture mechanics may be of interest, maybe not. It's most of the exam stuff is based on, or the quiz on linear elastic fracture. The nonlinear fracture mechanics is harder work. It requires a lot more stuff. So I guess let us then stop for the day and see you tomorrow.